Namaste and welcome to this lecture on mathematical foundations for machine learning. In the last couple of classes we looked at certain inequalities and we looked at the central limit theorem and towards the end of that last lecture we had a question. We kept talking about samples, but then we wanted to ask this question, look, does the sample have a geometry? If that is the case, we have most of our linear algebra concepts, we can apply that and then we can really do a lot of interesting stuff with the idea of linear algebra and matrices. So we said that does the sample have any geometry? What is it to say sample? Does the sample have any geometry? Remember when we talked about population, we said population is the entire set and sample is basically a subset that we are going to take out of the population. Now consider this example where we have a college, let us say an academic institution of let us say 10,000 students. Now I just want to figure out what is the average CGPA of the entire set of students who are there, like academic performance in terms of the average CGPA. I can't go and ask each and every student, I mean though the population size is 10,000 I could still do it, but then I prefer doing a sampling. Now what I do is I pick a sample of let us say 100 students and then what I ask is for these 100 students I ask them to list their CGPA. Now what I get is I basically get 100 measurements of CGPA, right. I get 100 measurements of CGPA. Now what I do is I try to get another sample of same size 100, but with a different set of students and then I try to get their CGPA. Now what I get is again I get 100 measurements of the CGPA. Similarly I will do some so many different samples of the same size 100 and I collect their CGPA from each of those samples of size 100. Now I get into something interesting, which means I am going to get that one parameter called the CGPA and what I am going to do is I am going to make 100 measurements of them. 100 measurements in sense I am taking from 100 different students. So I am going to make 100 measurements of them. That means I can actually look at it like a 100 component vector, right. Observation x1 is the CGPA of the first student, observation x2 is the CGPA of the second student and so on. Observation x100 is going to be the CGPA of the 100 student. That means I am going to have a 100 component vector. Now that is very interesting because what we did is till now we just considered the sample as a set of numbers or the set of measurements that you get or set of parameter values that you get and leave it at that. Now what we say is look, we can actually consider this as a vector, as an n component vector. Suppose you have n students and collect the CGPA of those n students, you end up getting an n component vector. The moment the idea of vector comes into picture, I know what to do. I would get into my ideas of linear algebra and then start putting those ideas here in stats and then try to learn it better and try to do better things, right. So what we are going to do is we are going to get into this idea of sample geometry right now. And then what we will do is we will slowly get into understanding the various terms that we saw in probability, which is typically in terms of variance, mean, standard deviation, correlation coefficient, covariance, everything. We will just get that in terms of our linear algebraic ideas or the vector space ideas or the vector operation ideas. So the focus of this lecture is going to be on sample geometry. What is it to say sample geometry? How does a sample look like what is it a sample, what do we mean by it? And then we slowly start putting certain ideas of the various terminologies associated with sample basically or sample statistics and stuff. We are going to put that here, we are going to obtain all these stuff in terms of linear algebraic ideas and that is going to be a very interesting interesting concept where we are trying to now bring in two different what would you call streams of or domains of mathematics together now, right. We are going to do that and in fact that is exactly why If you had seen read the textbook of Professor Gilbert Strang or any other professor who does a machine learning course, they always emphasize on knowing 3 important aspects of or 3 important mathematical domains for machine learning. One is linear algebra, the other one is probability and statistics, and the third one is multivariate calculus. We will actually see it in the next week's lecture. But here what we are going to do is we are going to look at sample geometry. That is great. Okay, so what are we going to do? Consider a matrix A. Let us look at this. Consider a matrix A. We will go from the idea of matrix to this sample rather than going from here, because we will be able to understand the idea of sample from a matrix perspective. So, I am going to say a matrix which is going to be of dimension, let us say n cross p, right. So, I am going to have a matrix which is n cross p, which means it has n rows and p columns, right. So, I am going to have something like this. Here is my matrix. I am going to have A11, A12, etc., A1p. Here I am going to have AN1, AN2, etc., ANP, right. Now, when we actually did this linear algebra, any time that you would have done, or probably the first few classes of this course, you would have seen that whenever we talk about this Ax is equal to b, this is where we started, Ax equal to b, we said that x is the set of unknowns, A is basically the coefficients, and b is basically the whatever output matrix that you have, right. X is basically the number of unknowns, that means the number of variables that you have. That number of variables, if you have a m by n matrix, then you have the number of variables to be n matrix, I mean n variables, that gets transformed, let us say be m cross 1. This is what happens. That means n columns are there, each column is associated with one variable, and that is the interesting inference that we have here. So, what are we going to do? We are going to say that, look, if I consider this as this is a matrix of say dimension n by p. Now, what I am going to say, each of these column corresponds to one variable, each of these columns. So, I am going to have p variables. So, p variables that corresponds to p columns, right, and I am going to have n rows. Now, what am I going to do? I have p variables, I said you have n p columns where I have recorded parameters, of I have basically collected p different parameters from a single person. Now, what I am going to do? I am going to collect p such parameters, p parameters from n such people. Is that clear? So, what we are going to do? We are going to say that I am going to get p parameters from each and every individual. Let us call this as S1, S2, etc. From the nth person or nth fellow also, we are going to collect AN1, AN2. That means I am going to collect p parameters from the nth guy also. Now, how do we represent? So, the n rows that you have, right, we have n rows. Now, that corresponds to n samples, n samples, right. So, now what we are going to do is, this is a very interesting understanding of a given matrix, of any matrix that you have. You can interpret the matrix as n observations of p variables. N rows p columns correspond to n observations of p variables. That means each observation is going to be a sample of a single measurement of p variables. So, we are going to write that. So, each row here corresponds to a single multivariate observation, we have p variables here. So, I will call that as a multivariate observation of or on p different variables. Right. So, you could even say that this is on the first trial. So, we will say taken in the same trial. Same trial or from the same person or from the same item or on the same item or the same person. Right. So, whenever I have an m by n matrix, I can always interpret that as m observations of n different variables. Each column will correspond to m observation of a single variable. So, let us write that. So, each column corresponds to, each column is basically n observations of a single variable of a single variable and each row is one observation of p variables. Right. So, the data matrix that you have, that you collect, where you collect all your parameters, each column corresponds to a parameter and each row corresponds to one observation of those parameters, whatever that you take. Right. So, we are going to say that each row, as I said, is a multivariate observation. So, what we are going to do is we are going to say, so this entire matrix that you get, right, it is often basically one particular realization of or say that we have a data which is basically a sample size of n. That is exactly what we have done. When we say n cross p, we say the data is basically of sample size n from a p variate population, right. So, we are going to say n by p matrix is nothing but it is a data of sample size n from a p variate population. This is what we have. Now, one more way where which you can represent there is another way of doing your representation, or there is other geometric representation that you have where you can say that okay, the data is nothing but p vectors in n dimensional space. So, you can actually even look at that. So, the other representation of data that we have, other alternative representation that we have is basically you consider the data as, let us say p vectors in n dimensional space. So, this is the other interpretation. So, let us see what actually it means. Let us just take an example and then see like what it is. Let us just consider this. We will also look at the idea of mean vector and stuff. We will also get another interpretation for the mean vector and so on. So, let us take an example. So, what I am going to do is I am just going to take a let us say let us consider a data matrix which is given by data matrix. I have x I will call this as this matrix X. I am going to take a simple example, let us say 4 1 5 and 2 2 2, or let us say 2 4 6. Let me make this as 4, so that division becomes easier. So, let us just make it 4. So, we have 4 1 4 and 2 4 6. Now, how did we interpret this? We said that look, this corresponds to one variable, this corresponds to one variable. So, basically what are we going to say? We can find average for this 3 observations, we can find average for these 3 observations, because that is exactly what we do. When you have when you collect data, what you do is you of the same parameter you can find out the average. Now, this is corresponding to variable, let us say x1, and that corresponds to variable, say x2. What we can do is we can find the average of these 2 guys, right. And once we find the average, we are going to we are going to put that average as actually vector, the mean vector that we are going to have. So, what we have, this is going to be basically 3 points in 2 dimensional space. I hope we get that clearly. 3 points in 2 dimensional space, x1 corresponds to 1, x2 corresponds to another 1. So, we have 3 points in 2 dimensional space. So, we would be able to, I mean, you can see it very clearly in you can visualize this very easily. So, this is going to be, let us say 0 1 2 3 4 5 1 2 3 4 5 and 6. Let us take this way. The first point is like 4 comma 2, 4 comma 2 is somewhere here, this is one point, then the other point is 1 comma 4, which is 1 2 3 4, this is another point, and the third one is 4 comma 6, 1 2 3 4 and here. So, these are the 4 points that I have. Now, I can find the average here. See, the average is going to be the vector x bar. I am going to put this as x bar vector, which is going to be, we know what it is basically this 4 plus 1 plus 4 by 3, and then we have 2 plus 4 plus 6 by 3, which is basically 3 and 4. So, where is 3 comma 4? 3 comma 4 is basically here. So, this is basically by x bar vector, right. This is one interpretation that we have, right. So, what we say is this is going to be the center of gravity or the balance point. So, this is basically the center of gravity. You remember we actually, when we computed the expected value of x, we actually said that look, expected value of x is nothing but the center of gravity, which is going to balance the point. You have you have these 3 points, this is the point where the scatter plot gets balanced, right. So, this is what we have. Now, the other way of looking at it is basically saying I am going to do it this way. So, I have the same set of points whatever we had here. So, what are we going to do? I am going to look at the same set of points, but what I am going to do is I am going to take this to be a 3 component vector and that to be a 3 component vector. Now, I am going to have 2 3 component vectors, which means I can now figure out again the average and so on, right. So, what are we going to do? We are going to say that look, these are the alternative representation which I said in the previous thing. You can say that the data is basically p vectors in n dimensional space. So, now what I can do is I can actually take p is equal to 2 in this case, p is equal to 2 vectors in 3 dimensional space. That is the other representation that I have, which means the representation is going to be again in 3D. So, this is basically x1, x2, x3 we have. Now, you can mark these 3 points 4 1 4 and 2 4 6. So, this will reside in a 3 dimensional space. So, that is what we have. Now, one thing if you observe here, I had my sample mean x bar, which is basically given by let us say x1 plus x2 plus I will say sigma xi by n, sigma xi by n, I is equal to 1 to n. Now, what is interesting is if we look at this, this is going to be x1 into 1 plus x2 into 1 plus etcetera plus xn into 1, divided by 1 into 1 plus 1 into 1 plus etc. plus 1 into 1. This is what we have. So, what is interesting is, if you look at this, this is of the form, suppose I take this xi to be the x vector, let us say xi the okay, I will take this n component xi, the n component vector, data vector, n component data vector, I will call that as let us say x. Let me take this as x, n component vector x. X vector. Now, what we see this average that you get here is basically the x vector dot product with the vector which is all component 1 divided by 1 dot 1, right. This is what we have here. It is basically the dot product that you see here, x1 y1 plus x2 y2 plus x3 y3 divided by, you can say it as y1 into y1 plus y2 into y2 plus yn into yn. Basically this looks like a projection, this is basically looking like a projection of the data vector. Where are we projecting? Projection of the data vector and where are we projecting? We are going to project, it says along or on to the direction, on to the, we are going to say equal angular vector, equal angular vector 1 right. So, this is what we are going to look at. So, the sample mean is basically nothing but the projection of the data vector along the direction of a vector whose all components are 1, right. That is what that is a very interesting finding that we have, which we probably covered in our previous lecture. Now, given this, the next question that I ask is like, oh, can I find the standard deviation and stuff. So, what are we going to do? We are going to make this statement, we are going to say that the average is basically the following. So, the average of n samples, right, average of n samples is basically, I will write this as 1 by n transpose, let us say the data vector, I will call the data vector as A. So, where A is the data vector or the measurements, basically I will call this as data vector or probably measurements, n measurements we have. Right. So, that is what is very interesting observation here. Now, the next one that we want to look at is, okay, I have done this. So, where is the standard deviation? How do I compute the what would you call, how do I compute my standard deviation and variance and covariance and stuff. So, let us look at this now. What are we going to do? We have the data vector. So, we have this. So, let us consider this. How do we get standard deviation, variance and so on. So, how do we get this? Okay, let us do this now. So, the first thing that I have is I had my data vector, let me call this as x1 vector. What was the x1 vector that we had there? We had 4 1 4. So, we had x1 vector was basically 4 1 4 and x2 vector was basically this, x2 vector was 2 4 6. This is what we had. Now, we know that our okay. So, the first thing that I want to do is I want to look at what is my mean vector x bar into the vector 1 1 1, right. I will take this as the mean vector. The mean vector basically for corresponding to this x 1 column I would have a lowercase x 1 which is basically the sample mean, which is basically 3, and here x 2 bar lowercase x 2 bar, this is a scalar, x 2 bar is going to be 4. Now if you look at this, what is interesting is I had my data which is 414. Now I want to find out how much is this data deviating from the mean. Therefore what should I do? I should basically subtract each of these data points from, I mean the mean from each of these data points. So I have to do 4 minus 3, 1 minus 3 and 4 minus 3, right. So I have to do 4 minus 3, 1 minus 3 and 4 minus 3. This is what I need to do. Basically I have x 1 vector minus, I will write this as x 1 bar into the 1 vector. I will take this as x 1 bar into the 1 vector, where x 1 bar is the mean that I had. Similarly I will also compute x 2 bar, I mean x 2 vector minus x 2 bar into the 1 vector, right. This is the vector here. Now what is that going to give me? That is going to give me the deviation that I look for, right. So what I have is I have my deviation vector d1 which is nothing but my x 1 bar vector, this is also going to be a vector, minus x bar x 1 bar into the 1 vector. Similarly I am going to have the deviation vector d2 which is given by x 2 vector minus x 2 bar into the 1 vector, right. That is going to be my deviation. So what am I going to get here? So this is going to be, I have 4 1 4 minus 3 3 3 and I have 2 4 6 minus 3 3 3 minus 4 4 4, right. So what do we get? The deviation vector is basically 1 minus 2 1 and the deviation vector here is going to be minus 2 0 2, right. This is what I have. Okay. Now what does it mean? It means I have a vector, let us say x 1, I have this vector, let us say x 1 vector, and I have this vector which is nothing but x bar in x 1 bar into 1 vector. This is going to be my deviation vector which is going to be x 1 vector minus x 1 bar into 1 vector, right. So that is going to be the deviation vector. So what do I have? I have projected this x 1 vector along the direction of 1 vector and I got my x bar which is my mean, and the difference between the x 1 vector and the mean vector is going to basically be my deviation vector, right. And it is very interesting if you can actually check it out, you can actually see this, the x bar x 1 bar 1 vector dot product with this d 1 vector is always equal to 0. X 1 bar vector with the dot product with the d 1 bar vector or the d 1 vector is always going to be 0. That means these two guys are perpendicular, right, and that is a very interesting stuff. Similarly I have x 2 bar into 1 vector dot product with the deviation vector is 0. That means what are we going to say? I am going to say that the mean vector and the deviation vector are orthogonal to each other, and deviation vectors are perpendicular to each other. You can check with even the other vector, so you would get this, right. Now what I am going to do is something interesting. I am going to look at the squared length of these two deviation vectors. I want to find out what is the deviation vector d1, the magnitude d1 dot d1 vector. That means I am going to look at the squared length of the two deviations, which is nothing but that is something which we know. What is that? This is nothing but, let us say, xji minus xi bar the whole square, sum of squared deviations. This is what I have, j is equal to, let us say, 1 to n, right. This is what? This is basically sum of squared deviations. And what is this? This is going to be length of the deviation vector square. Length of deviation vector square is basically going to be the sum of the squared deviation. And what are we going to say? Now you take the squared, you take the square root of this. What are we going to say? We are going to say that the length, what we are going to say is the length of this deviation vector, length of the deviation vector is proportional to the standard deviation. To the standard deviation. So, we have sum of squares, we have here sum of squares, sum of deviation squares, and we know that when you divide it by n you are going to get the variance. Now you take the square root of it, you will get the standard deviation, and therefore what we say is, look, except for the division by n, or when you take square root, it is going to be square root of n, division by square root of n. Therefore we are going to say that the length of the deviation vector is proportional to the standard deviation, which is a very interesting finding. We interpreted the sample in terms of a vector, and then what we did is we looked at, we said that okay, this is going to be an n dimensional vector or a p dimensional vector, whatever it is, and then we projected this p dimensional vector onto a vector which is equiangular vector. That means it is going to be we are also looking at the vector all components whose all components are 1. We projected the data vector onto the all components 1 vector, and then the projection was basically my sample mean. Now when I wanted to subtract the sample mean from each of my observations and then square the do the sum of squares of deviation, I end up getting my variance, and take the square root of it, you end up getting your standard deviation. Therefore I am going to say that the length of the deviation vector that I have is proportional to the standard deviation, because that proportionality thing would be that square root of n which you get. That is a very interesting finding, which means now I started with samples, we made observations, we put that observation as an n component vector, okay, that is done. I was able to get the mean in terms of a geometric projection, fantastic, I got it. I subtracted the mean vector from the actual data vector, I got my deviation vector, and that deviation vector, the length of the deviation vector turns out to be our standard deviation, which is a very interesting finding. Now what we want to do is we also want to find out the cross terms, like what happens when I do the dot product of one vector with another vector. This basically gave me the standard deviation that is there in the first variable. This, the length of this is going to give me, if I take d1 dot d1, this is going to be basically my let me just take this as di dot di. So that will correspond to what is the vector that I am looking at. So di dot di. So what is this going to give me? This is going to give me the variance, square root of which is going to give me the standard deviation for that particular variable. Now actually I can continue to do this and then get the standard deviation for each of those variables. That means if I have p variables, all I need to do is project each of those p vectors onto the vectors which whose all components are 1, subtract this projection, the deviation vector you will get, take the square root of take the length of that vector, you end up getting the standard deviation corresponding to each of those p variables. That is very interesting, right. Now what I do is I want to look at this, let us look at what is di dot dj. that means I am going to look at the dot product of two different vectors, right. I am going to look at, okay, let me put this as di dot dk for some reason, I will come to it. So, I want to look at di dot dk, that means the dot product of two different vectors I am going to get. Now, what is this dot product of two different vectors? So, I have di, let me take d1 and d2 for example. d1 was nothing but x1 minus x bar into 1, x2 minus x bar into 1, I will say okay, x bar, okay, I will take this as x1 minus x1 bar, x2 minus x1 bar, x3 minus x1 bar. d2 is basically, let us take it as, okay, I will put this again, I will make one more change, sorry, bear with me. So, it is going to be x1 1, x2 1, x3 1. Now, what I am going to do here, I am going to take this as x1 2 minus x2 bar, x2 2 minus x2 bar, x3 3, I mean x2 3 minus x2 bar, this is what I get. Now, what I am going to do is I am going to look at dot product of d1 with d2. Now, what is that? It is x1 1 minus x1 bar into x1 2 minus x2 bar plus x2 1 minus x1 bar into x2 2 minus x2 bar plus x3 1 minus x1 bar into x3 x2 3 x, okay, this is going to be x3 2, sorry, this is x3 2, this is going to be x3 2 minus x2 bar. Now, what does that look like? That actually looks, that is exactly what we will do in terms of our covariance. This is going to be xi minus x bar into yi minus y bar, that is what we do, that is precisely what we have here. So, this is going to be equal to summation j is equal to 1 to n xji minus xi bar that is the mean for that ith variable xji minus xi bar into xjk minus xk bar. Right, that is interesting. So, this is the term that we are looking for. So, what we have? We had di, okay, let me put this as di dot dk. So, this is what we have. So, what are we going to do? We are going to look at this as, okay, so I am going to write this as sigma xji minus xi bar, the mean value, into xjk, that means every sample value, minus xk bar, the mean of xk. This I am going to write this as square root of, we will see why, how does this come. So, we are going to say this as square root of sigma j is equal to 1 to n xji minus xi bar the whole square into square root of sigma xjk, j is equal to 1 to n xjk minus xk bar, the mean, the whole square, and I am going to get a cos theta of cos of theta ik. What is the angle between these two vectors? Cos of theta ik, where I am going to say the deviation vector, what we had di dot dk, we already know what is this di dot dk. How do we do it? A dot b is nothing but ab cos theta. Recall that a dot b is nothing but magnitude of a, magnitude of b, and cos theta. So, now what I have di dot dk, which is nothing but the magnitude of di, the ith deviation vector, the magnitude of kth deviation vector into cos theta, where theta is nothing but the angle between the ith data vector and the kth data vector. This is what we have, and that is exactly how we got this. right. So, what are we going to get? I am going to talk about my correlation coefficient here. Correlation coefficient is nothing but correlation coefficient is nothing but this. I am going to call this as di dot dk. Let me give a name to this. I am going to call this as SIK. So, I am going to write this as SIK. So, this is going to be S into IK divided by square root of SII into square root of SKK. I am going to have that is equal to cos theta IK, and this is what I am going to call as the correlation coefficient between the two values, which is basically rho IK, right. So, what we see is the what is a very interesting finding that we have here. SIK is basically the dot product of di dk, whatever that we have written here. So, this is going to be j is equal to 1 to n, right. This is what we have. So, what are we going to say here? When I say that both the vectors are in the same, they have the same orientation, we say that the sample correlation is going to be close to 1, right. That means if they are in the same direction, that means as one increases the other fellow will also increase. In that case, the correlation will be equal to close to 1, and when they are in the opposite direction it will be close to -1, and when they are perpendicular, nearly perpendicular, then the correlation coefficient is going to be 0. Now, what we have done, this is very interesting, we have looked at sample, we looked at sample in terms of vectors, and then we said that look, I can even get the standard deviation, variance, correlation coefficient. You tell me what we get everything from looking at the geometry of the sample, and that is the most important stuff. So, what are we going to do? I am going to just write one more stuff and we will wind up this class. We are going to say the geometrical interpretation of a sample. So, let us write that geometrical interpretation of the sample, which means now we understand what is it to say sample geometry, we understand the sample also from the geometric perspective. So, I am going to say geometric interpretation of the sample. Right, we are going to do this business. Okay, so, what is that? The first point that we are going to say is look, number 1, projection of a column, let us say xi vector here, this is going to be a column vector. So, xi vector of the data matrix onto the equal angular vector 1 is the vector xi bar into one vector, where xi bar is the mean, right, and xi bar into one vector has length square root of n times magnitude of xi bar. The length, therefore, it is going to be xi bar, square absolute of xi bar into square root of n. So, what are we going to say? The sample mean, the ith sample mean, this implies ith sample mean is related to the length of the projection, projection of the ith column let us say xi vector, this is the ith column of the data matrix, on to the one vector, right. Okay. Now, the second important understanding that we are going to get is this. We are going to say the information what we are going to call is basically the matrix whatever we have, the correlation matrix and the covariance matrix. We will come to that in a bit. Okay. So, variance covariance matrix which we will do, but I will just make a note here. We will say that the information comprising the variance covariance matrix is obtained from the deviation vectors. From the deviation vectors which is given by di is equal to, di is a vector whose components are basically given by the xi vector minus xi bar please follow up with the notation here, one with an arrow I am drawing which is basically the vector, the other one is with the bar that I am taking which is a scalar quantity which is the sample mean into one vector, right. This is what we have, and the squared length. So, I am going to look at the squared length of this vector is basically nothing but it is n times the standard deviation of the vector, and I am also going to look at the what do you call the dot product of di dot dk which is given by n times Sik, where Sik is basically the covariance, right, and the sample correlation. So, this is Sik is basically the covariance, Sik is okay, Sii is standard deviation and Sik is basically the product of these two vectors. That means the dot product, the component wise multiplication of my deviation values, right. So, that is what it is, Sik is that, and most important stuff is the last one where we say the sample correlation is basically the cosine of the angle, cos of angle between the two deviation vectors di and dk vectors. So, this is very interesting that we were able to bring in a complete geometry of the what would you call, we were able to get the complete geometry of sample, and we looked at all the parameters associated with this sample in terms of the mean, variance, standard deviation, then the covariance, correlation, everything from the linear algebraic idea or the vector space ideas within our products and stuff. That is a very interesting finding that we have, that is very that actually will help you visualize things. So, it is going to help you a lot when you do visualization, I mean when you can look at data and then say look, there are in fact when we did correlation, we said correlation coefficient is covariance of x y divided by variance standard deviation x standard deviation y. We actually were looking at this, we said that the covariance is going to be like dot product, and the correlation coefficient we said it is a value between -1 and +1, and we also said that look, there is something in the vector side which will also be equal to between -1 and +1. We said that cosine of the angle between two vectors, that is exactly what we see here. On that note, what we will do is we will conclude this lecture on the sample geometry, and in the next class we will look at the covariance matrix, which is very essential as far as your data is concerned. You will keep coming across covariance matrix in your machine learning and data science very often, and we are going to look at properties of the covariance matrix. We will see how to get the covariance matrix, and then we will look at what are the properties of the covariance matrix, and with that this module will get over. We will be starting with the next module on vector calculus after the next lecture on covariance matrix. Namaste.